I guess we can start. Hello, everyone. Good afternoon and welcome to our today's seminar this afternoon. And good morning, good afternoon to those who are joining us live and virtual. This is the fourth seminar of our hydrogen seminar series organized by the Clean Combustion Research Center. Today, our seminar is titled Hydrogen Safety and Transport Technologies. And today we have our moderator, Dr. Steve Olegheri. He is a science specialist in the carbon management R&D division in Saudi Aramco. Steve, I know him. He has more than at least 20 years plus of experience in hydrogen, and more specifically in hydrogen separation from hydrocarbons and ammonia. He holds several patents, several publications, a book chapter on hydrogen. So without further ado, I would like to welcome Steve to introduce the panel and the speakers. So Steve, thank you.
Good afternoon, everyone, and or morning or evening, wherever you are online. And I'd like to welcome our in-person participants. Thank you for coming this afternoon. I'd like to start off right away by introducing our first speaker, Nick Barillo. He is the Executive Director of the Center for Hydrogen Safety at the American Institute of Chemical Engineers, AICHE. He is also the Hydrogen Safety Program Manager at the Pacific Northwest National Laboratory. As such, he is an expert in hydrogen safety, which is the topic of our first of the three presentations that we'll be seeing this afternoon, followed by question and answer session and discussion. So without any further ado, I'd like to kick off our first speaker. Thank you.
Thank you for the welcome and greetings, everyone from Washington, D.C. I'm at the Hydrogen Americas Summit here in D.C. and have been communicating with lots of folks from all around the world. So it's great to have this opportunity to share with you this morning as well. A little bit about my background. I'm a fire protection engineer by training and have been involved in hydrogen about 15 years. And so I'm going to take you through some hydrogen safety considerations. And we'll move fairly quickly. There's a lot of slides. I tend to do my presentations fast and let you go back and look at the information later. So feel free to do so. All right, well, we know hydrogen's got great potential. It's certainly used in many different applications, some of which you could see here. Trending for Google relative to the term hydrogen, you could see over the last 4 or 5 years has really grown significantly. We probably could all recognize the need for safety with hydrogen, but just to give some background, safety issues could be a deal breaker if they're not successfully addressed. We start out with hydrogen with a really strong foundation. It comes with nearly a century of industrial use, lots of good safety knowledge, best practices that exist. However, its use as a fuel and an energy carrier is certainly new to many who may not have the experience or expertise for its safe use. Lots of misconceptions, and people may not know what they don't know. So we see these assumptions coming up, things like we don't know how to use it safely, where do you know how to use it safely, or it's just like any other flammable gas, or it's too dangerous. Failure to address these gaps can result in incidents and industry setbacks. So considering incidents, some other industries that have had significant setbacks as a result of those incidents was the airline industry, the chemical industry, and the space industry. And these incidents here, the Bhopal, India incident with 3,800 people being killed, and certainly the space shuttle incident was incidents that have set back the chemical and space industry quite a bit. And so we don't want to see the same thing happen. Hydrogen, this is the last few years, some incidents that have occurred. And there's really a common thread here, things like not understanding the electrolyzer membrane gas permeability and its operation, an assembly error on an end plug, an incorrect pressure relief device installed, unauthorized repair and failure to follow procedures, and an incompatible pressure relief device. So you ought to see that the common thread here in these incidents is human error. And that's not just true for hydrogen, but it's also true for other industries as well. So there's not a unique thing here with the hydrogen industry, but some of the others include 90 to 95% cybersecurity, nuclear industries. And you can see some of the other numbers there on the right as well. All fuels contain energy and can be hazardous if handled improperly. Here you see some information on gasoline and natural gas that we're probably all very familiar with. The number of injuries and deaths, and this is just a small section that have been looked at in number of years and locations, and yet the losses were pretty high. But we've grown comfortable, if not complacent, with these fuels. So let me jump into hydrogen, its properties and behavior. It's a gas at ambient conditions. It rises and disperses rapidly. Flammable range is 4 to 75% in air. It's a liquid at minus 253 C. It's a cryogen. You can't get to that by compressing. It's only by chilling. And you see that when it expands, it's about 850 times when transitioning from that liquid to gas phase. Energy content, a kilogram of hydrogen is approximately equal to a gallon of gasoline. You can see the numbers there. Some additional properties, it's colorless, odorless, tasteless, certainly recognized as flammable, non-corrosive, can be an asphyxiant, but all gases can in the right concentrations. It is a combustion hazard, and its use as a fuel results in really in pressure hazards as well. Cryogen can be a low temperature hazard. Embrittlement, also certainly a factor with hydrogen, and we'll talk a little bit more about that as we go here. Comparing hydrogen to some of the other fuels, you see natural gas and gasoline here. Probably the one that jumps out a little bit is the odor, where natural gas has those mercaptans and gasoline has the benzene and other additives. Hydrogen is naturally odorless. Lots of work being done to try and come up with an odorant. There are some challenges. It's the smallest molecule. It's also very buoyant, so it wants to move up and away from other molecules. The other problem is that if we use something to odorize it, we need to make sure that those odorants are not going to cause problems in equipment such as fuel cells. Another line here that I'd like you to highlight on is that minimum ignition energy. You can see the energy needed to ignite gasoline and natural gas about an order of magnitude or so higher than hydrogen. So very easy to ignite hydrogen. High pressure leak can also auto ignite. Comparing some of the other properties, just looking there on the right, you see hydrogen and the impact of the vapor density, very buoyant. And you can see what happens with the things like propane and gasoline that'll hold near to the ground. Hydrogen will move up and away very quickly. The flammable range, both in air and oxygen, you can see there. Really, the left part of those bars, though, are the ones that are the most significant for the fire and combustion hazard. It's that lower flammable range, and you can see propane actually has a lower flammable limit, and methane is very similar to hydrogen as well. Burning velocity, gases with high burning velocities can really generate potentially damaging explosion pressures. And here, what I'm trying to point out in this bar graph is that it's just so much greater for hydrogen than some of the other gases, and this is one of those properties that makes hydrogen unique, and we need to be careful with how we use it and how we protect. Some other characteristics, because it's a small molecule, small leaks are somewhat common, and most are insignificant. So when you're getting a very, very low weeping around a joint, perhaps, still needs to be addressed and fixed, but most of the time it doesn't create a hazardous scenario. So hydrogen, under most of the pressure scenarios, will move in the direction of the leak. You can see here a figure on the right in which this is taken from the HiRAM model, a jet flame coming off of hydrogen, and it'll go out that distance until the pressure dissipates, and then it'll move up and away as hydrogen will in a more ambient condition. High pressure leaks can lead to explosions under jet flames, and there's a fairly new phenomenon that's really been starting to be addressed, which is this jet flame explosion or jet release explosion, where they are seeing even without obstructions or other conditions, they're seeing jet flames can result in explosions fairly quickly. So safety, it's there's certainly a lot more than 3 parts, but I want to focus in on for this discussion about 3 parts. It's codes and standards and regulations, best safety practices, and then a culture of safety, which is that being invested in safety. And so I want to really keep that in focus as we go through. We're going to look a lot at the middle piece there, but certainly codes and standards play a significant role in ensuring that the public is protected, and that there's a confidence and a consistency to how requirements are applied. Safety culture is also very important as well, as without that culture of safety, we're going to end up in incidents and a failure to really take the necessary precautions to make sure that we're working properly around hydrogen. Safety planning should be a part of anything we do, and I want to emphasize this in the beginning. So whatever the hydrogen project or activity that you might be involved in, really safety planning is an important part of the process. It's essential to protect people, and certainly to minimize damage to facilities, also to protect an organization's reputation, and to help the industry progress without any major setbacks. The document you see here is available through that link. It's a free download meant to help projects in doing safety planning. So let's jump into the safety basics. It's a flammable gas, and like all flammable gases, there are some really basic considerations, like certainly defining mitigation measures, eliminating hazards, system integrity, always important with a gas, proper ventilation to prevent accumulation, managing discharges, this is intentional discharges, not accidental, detecting and isolating leaks, and then training personnel. I'm going to jump into just a few items. There certainly are a lot of considerations for how to address and handle hydrogen safely, but I'm just going to cover a few that tend to come up quite a bit in our discussions. So ventilation, very important. If you have an enclosure, there are some times when you can do a passive ventilation, but active ventilation is really the best approach. And some things to think about when you think of active ventilation. So the ventilation system itself can't provide a source of ignition. So you need things like non-sparking fan blades and electrical equipment that's classified for that environment. You want to make sure that ventilation system's operating at all times when the hydrogen's present or could be accidentally released. If you need to shut down the ventilation system for maintenance or other activities, really you should isolate the hydrogen as well. Leak detection is a big part of what we discuss. It may be required by a regulatory agency or provided just to enhance the safety of the operation. There's lots of different ways to go about leak detection. Perhaps the most common is a spot detector approach, and here you see an image on the right here. That top device there is one of the hydrogen detectors. That's great, except for you really have to have a good determination of where those leaks might be and get those detectors fairly close to where the hydrogen will accumulate. Another approach is to monitor internal pressures and flow rates for piping systems. This is so if you have a system where the flow rates are going to be a certain number or a certain rate, and the pressure is going to be at a certain number, then you can really monitor and see what an off normal is and then detect. Doesn't work very well where the flow rates or pressures are variable, for instance, in a laboratory setting where different users are using it at different times. Another method is to put a pipe within a pipe and monitor that annulus for hydrogen. Checking for leaks manually, extreme caution should be utilized. Hydrogen in its pure form is nearly invisible flame. Many cases where there's accidental fires, the flame will be visible when it entrains other materials that might be burning as well, or dust or dirt, those sort of things. But best approach is to have a flame detector or thermal imaging camera. Listen for venting gas, watch for thermal waves. A combustible probe, such as a broom, could be used. And a couple considerations where you have multiple gases, be sure to investigate the most significant hazard first, and then work your way back and allow enough time to to really determine what caused the leak prior to going back into that area. Emergency shutdown system is another big part of what's needed for hydrogen. So it should operate on detection of manual detection or fire alarm, loss of ventilation, those sort of things. De-energize unclassified electrical. Most times it should keep the ventilation running. And then automatic shutoff valves for the supply of hydrogen should be isolated back, that sort of thing. And then where you place those switches is often very important to consider. In this case, on the picture on the right, you're seeing the red button there is the emergency off switch. The challenge here is that the dispenser for the vehicle is on the left of that, so a car door could hit that switch and accidentally trip the system. Selection materials, I mentioned that embrittlement is an area of concern for hydrogen. And so really important to consider the type of materials. Austenitic stainless steels are about the best, aluminum alloys, copper and copper alloys. At the end of the day, it's really important to know what your use condition is and to have the materials for that use condition. For liquid hydrogen, it can cause serious frostbite and hypothermia. Ice can form on vents and cause them to malfunction. Certainly, condensed air can result in oxygen enrichment and explosion conditions. Ice may form and plug lines, and then certainly evaporation generates a cloud, and that cloud could flow downstream with ignitable concentrations of hydrogen. So lots of things to think about with safety. This was just a few. I did want to point out a few resources for you to think about as you go forward in what you're doing. And really, it all comes down to communication. Been involved in this for a long time, and while there are technical issues, I think one of the challenges we have that getting that safety information to the right people to do their jobs is really a significant issue in what we're doing. So the Hydrogen Tools portal, want to point that out to you, as well as the Center for Hydrogen Safety that I'm a part of. Some resources available to you. The Hydrogen Tools portal is it's got lots of resources in one place, things like lessons learned, best practices, training materials, analysis tools and codes and standards and that sort of thing. The center that we're really trying to bring this material and best practices worldwide. You can see some of the resources at the right. It's for all use of hydrogen. It's really meant to develop a community around hydrogen and doing it safely. This is our current membership. Shout outs to Saudi Aramco for being a part of the Center for Hydrogen Safety. And you can see we're growing very quickly as well, and welcome your organization to join us if you see some value there. I'd love to talk to you. So also wanted to point out some educational materials. These are available through the URL listed there up at the right. There are 3 types here. There's some traditional e-learning on the left, and a credential that goes with that, some first responder courses, and then we routinely do webinars, and we make those available to our membership. It's free the day of, and then pay for product later on. Working groups, we're really involved, and I wanted to point this out to show that there are some serious topics that we're working on right now, things like university setting for hydrogen safety, as well as hydrogen safety culture, failure rates, and blending of hydrogen is also a big one. Invite you to follow us on LinkedIn to hear more about safety and safety issues and what we're doing, and as well as some tools and resources that may be beneficial to you. And then also invite you to our upcoming webinar. This is again a free webinar, and this one's on transportation safety with hydrogen and a global perspective on that. And we're certainly going to be back in Europe in May for a conference. We just had a conference in the US last month, very well attended, and lots of great discussion. So I'll finish up by saying that, with the promise of hydrogen comes the responsibility of safety. The applications are going to grow. Safe practices are needed and to be disseminated. Certainly there's some good tools out there to help you out with all that. So thanks for the time to share. Look forward to your questions and hearing what your thoughts are as well.
Thank you very much, Nick, for setting the stage. Obviously, safety is paramount for public acceptance and implementation of the hydrogen economy. So that's basically lays the groundwork for our next topic, which is hydrogen transportation. Professor Mani Sarathy is in the chemical engineering, and he's also associate director of the Clean Combustion Research Center at KAUST. So he is currently also senior manager of technology and innovation at Enowa Hydrogen and Green Fuels. So welcome, Professor Mani, and I'd like to go ahead and proceed with your presentation. Thank you.
Okay, good afternoon, everybody, and nice to be with you all. So today I'm speaking to you from NEOM, and I wanted to talk more about hydrogen storage and transport, and also in the context of NEOM, what makes sense to us here at NEOM or also in Saudi Arabia to implement from a technology perspective. So you can pretty much divide your hydrogen storage and transport technologies into several key categories. Mechanical storage, let's say physical materials-based storage, and chemical material-based storage. And on the lower right, we have a chart which shows us the volumetric hydrogen density. So the amount of hydrogen in terms of mass, kilograms of hydrogen per unit volume, and then also the gravimetric hydrogen density, the weight percent of hydrogen in different types of storage mediums. You can see here on the top right, diesel and petrol, they have very high volumetric hydrogen density because they're hydrocarbons, also very high gravimetric. Things like metal hydrides, these are metals that could be hydrogenated and dehydrogenated. They're typically very good in volumetric energy density, but very low in gravimetric because the metal weight is quite high. Common technologies are compressed hydrogen. We'll talk more about those. Liquid hydrogen in the tank, and also other types of liquid organic hydrogen carriers. So if we look back at these three different areas, mechanical storage, I think we'll hear a lot about it also in the next presenter. It's when you take cryogenic compression techniques to cool down and compress your hydrogen and transport it as a liquid. One of the major issues with this is you need cryogenic vessels. You need to maintain the vacuum stability. And physical material-based storage, these are what we typically use for storage of hydrogen today in short duration, short haul transport, carbon fiber composite vessels. But future, people are looking at high strength polyethylene as well, and new types of pipeline structures for materials, to physical material storage. And chemical material storage is anything related to a liquid hydrocarbon, a porous material, or a metal organic framework, even things like ammonia, methanol, formic acid, as well as the metal hydrides. So we'll talk a bit more about each of these in more detail. So hydrogen storage, of course, has been around a long time. Hydrogen is stored in refinery settings, in vessels. It's transported typically in steel cylinders for shorter distances. For long distance transport of hydrogen, it's a relatively new area of interest because the idea is to move hydrogen from areas where it's produced, such as Middle East and North Africa, to regions of the world where it's needed for demand, such as Japan, Korea, and Europe. And these are some articles we've seen recently in the past few years. So Kawasaki, together with the Australians, are piloting liquid hydrogen tankers, one liquid hydrogen tanker moving hydrogen from Australia to Japan. Saudi is exploring the option of green hydrogen via a pipeline to Europe. And other companies are looking at new types of technologies for ships, such as Hyundai Heavy Industries. And this is just to name a few. And we'll talk a bit more about these different technologies and when they make sense and when they don't make sense. So the first, hydrogen compression and liquefaction. As we mentioned in the last talk, it cools at -253 C. So below 240 C, you can typically compress the hydrogen and liquefy it. And this is a schematic of the system from Kawasaki. You basically have a cold box, and inside of that cold box, you have a complex network of heat exchangers and an expansion turbine to get you down to the temperature that's required. Interestingly, they use liquid nitrogen for the cooling. And then also they use hydrogen for the cooling. Hydrogen gases pass through an expansion turbine which gives additional cooling to cool down to that minus 253 C. And then the tank has to hopefully have good insulation to maintain the cold temperature. Of course, the cryogen doesn't last forever, so the lifetime is limited, and a lot of the design and fabrication and engineering of the system is to extend the lifetime of the cryogen inside of the tank. For large-scale hydrogen storage, it's most likely to be up underground. So let's imagine we're making tens of thousands of tons of hydrogen per day. In that case, it's going to be unlikely that we're going to store it in above ground vessels. So today, the main methods for storing hydrogen in very large volumes are subsurface structures. These can be rock caverns, salt caverns, or even underground pipes. Basically drill a hole down, install a steel casing, and put a valve on the top, and you can compress your gas inside of this valve, inside of this chamber, and the earth basically acts as your pressure containment system. On the bottom right chart, this is a nice graph from a company out of Australia called Ardent Underground Hydrogen Storage. Their basic concept is, again, drilling down large bores into the earth, lining it with cement, capping it off, and using that as a hydrogen storage vessel. And the graph is nice because it shows us the approximate cost. This is Australian dollars, cost of hydrogen stored per kilogram, together with the amount of hydrogen that's being stored. So technologies like tube trailers and pressure vessels, these are very expensive in terms of amount of the cost per kilogram of hydrogen, and they're only useful for, say, maximum 1 ton or up to, say, 10 tons of hydrogen. After that, you got to go underground or go to a very large cylinder bundle. Underground pipe storage, anywhere upwards of 10 to 100 tons. And these types of pipe storage systems where you line basically a hole in the ground, you can get anywhere from 100 to 1,000 tons of hydrogen. After that, when we're talking about really large amounts of hydrogen, upwards of nearing 10,000 tons of hydrogen, you're going to have to go to a natural structure like a salt cavern or a network of salt caverns. And this will be relevant because some parts of the world will do seasonal storage. They might make several thousand tons over the course of a summer of hydrogen, and they want to store that for 6 months to use in the winter time when there's less renewable energy available. So large caverns like salt caverns and rock caverns will become relevant. And you will choose the type of underground storage based on your production target, as well as when you plan to use that hydrogen. At smaller scales, the technology is quite mature already. Essentially, what we have is lightweight compressed cylinder storage. This is today the most effective, cost-effective, and lightest way of transporting hydrogen over short distances. This is what we use in NEOM now for hydrogen storage at small scale. Again, this is in the range of hundreds of kilograms to several tons. Essentially, it's a carbon fiber composite vessel with a polymer liner. The reinforced shell allows for corrosion resistance. It's lightweight, and it can contain the pressure. These vessels are type 4. They can go up to 700 bar, and they're much lower in weight than your typical steel vessel of comparable or rating. A typical 700 bar tank, type 4, would require 10 kilograms of carbon fiber per kilogram of hydrogen. If you have a vehicle might carry about 5 to 6 kilograms of hydrogen. So then you need about 60 to 70 kilograms of carbon fiber to be used inside of that storage vessel. And there's a lot of discussion now about the global carbon fiber market. Actually, if we look at expansion of hydrogen production and hydrogen utilization, and the demand then will be for these hydrogen storage cylinders, there'll be a huge increase in the amount of carbon fiber that's needed. And the carbon fiber industry has to scale up significantly to meet that demand. Besides these carbon fiber vessels and underground storage, another way to transport hydrogen is using liquid organic hydrogen carriers. These are essentially chemicals and organic compounds that are able to store hydrogen. The general concept is shown in the top left. If you electrolyze water or make hydrogen from natural gas and capture the CO2, you can take that hydrogen and you can hydrogenate a molecule. Your simplest example is a molecule like toluene. Toluene is an aromatic, and if you add hydrogen to it, you will get methyl cyclohexane. So you hydrogenate. The hydrogenation process is exothermic. It releases heat. You can then move that methyl cyclohexane just like an oil or a liquid. The picture on the bottom shows you these types of LOHCs. They're liquids, they're clear. They might have a color when they're unloaded, and then when you add the hydrogen, they can change color because the material properties have changed. And then when you move that liquid to another destination, you add heat. It's an endothermic process, and you release the hydrogen and you regenerate your toluene or your LOHC carrier molecule. And then that hydrogen, which is removed from the LOHC, can be used for mobility applications, fuel cells, industrial processes. You can get a rather pure form of hydrogen. The advantages of this kind of system is, as you see on the top right, the amount of energy that you store in these LOHCs is quite large, much larger than you would carry in a battery or thermal energy storage system, and could be nearing the energy density of liquids like gasoline and diesel. Common LOHCs include things like methanol. Methanol can be made from hydrogen and CO2. You can then dehydrogenate methanol, formic acid. Dibenzyltoluene is the one today that's gaining the most commercial interest. You can move all these molecules over long distances as liquids. They're easy to store. They're rather safe. And even some studies are reporting that LOHCs are cheaper than pipeline storage over long distances, 5,000 kilometers and long durations. And the reason for that is pipeline infrastructure is quite expensive. And also in pipeline infrastructure, you have to add compressor stages, adds additional cost. And for long durations, pipelines can also be prone to leakage. Whereas LOHCs have the advantage that you can use existing vessels, you don't worry about leakage, but you do have the challenge then of recovering the hydrogen and needing heat for that process. So if we look at today, when companies like NEOM look at look at exporting hydrogen, of course, there's ammonia. Ammonia, I'm not going to talk much about because we've heard about it in previous seminars. The alternatives are liquid hydrogen and LOHC. So liquid hydrogen, again, cryogenic, significant infrastructure requirements are needed. You need spherical vacuum isolated tanks. It's not as simple as just taking existing liquefied natural gas infrastructure and changing it to hydrogen. Entirely new infrastructure and specific infrastructure is needed because of the different temperature requirements. So we need to build essentially hydrogen liquefaction terminals at places of export, and at places of import. We need, of course, the degassing facilities to import. So you need a corresponding liquefied hydrogen terminal to bring in the material. And then also we'll need very special vessels with specialized vacuum tanks. And one advantage potentially is that these vessels, the boil off of the hydrogen during the transport could use partially for powering the vessel. LOHCs, on the other hand, such as methyl cyclohexane, dibenzyltoluene, they're very easy to transport. You can use existing floating roof tanks. Infrastructure requirements would be very minimal. The major challenge is you have to build your dehydrogenation infrastructure. So at the point of use, you will need access to waste heat, or you'll need a very efficient way of either burning hydrogen to generate heat for the dehydrogenation, or getting energy input from other places. So I'd like to talk more specifically now in NEOM context. What are some of the things we try to think about if we want to export hydrogen in things other than ammonia. So again, we have options of a pipeline. We could look at those derivative molecules like LOHCs and LH2. And then we can also look at potential destinations where this material has to be transported to. So again, the state of the art today, if we were to make a decision, and the decision for the first plant for large-scale hydrogen production and export is ammonia. You combine hydrogen with nitrogen, you liquefy it around 6 bar, you transport it by ships, and you need to develop an infrastructure for recovering the hydrogen back from the ammonia by cracking. And we heard about that process a few lectures ago about ammonia cracking to get hydrogen. The tankers are pretty well established for transporting this material. Now, LH2, again, we said it's much lower temperatures. You need to pressurize and liquefy it. The ships do not exist today, but there's no issue for reconversion. The LOHCs, we can make them today. The ships are available. The transport is pretty straightforward. We just need to identify the energy sources for recovering the hydrogen at the point of use. And then pipelines are simple in terms of process. All we need is a pipeline infrastructure, but pipeline infrastructure for hydrogen, either onshore or offshore, are not very extensive these days. And we'll see in the next slide potential challenges around building this infrastructure. So let's take a simple example. And momentum is building in Europe and Japan, mainly to import hydrogen by ships. We see the port of Antwerp, also port of Rotterdam, looking at import facilities. There's a study underway in the EU on the feasibility of large-scale commercial import of hydrogen, both by LOHC and by liquid hydrogen. There's a pilot projects in Japan and Australia, which we mentioned previously about LH2. So I think for the next 10 years, the shipping routes for hydrogen will expand, liquefied hydrogen as well, LOHC and ammonia. There'll be a lot more R&D needed to make these supply chains more effective and cost-effective and safe, and a lot of need for improving the storage technology to reduce the losses during the transportation. Beyond 10 years, if there's a hydrogen economy takes off and there's sufficient leadership from the countries that are producing hydrogen as well as the ones that are taking the largest demand, pipelines could become realizable infrastructure development projects. So thank you, and we can have a discussion about these topics afterwards.
Thank you, Professor Manny, for the comprehensive overview of hydrogen transportation and storage. It's great to find out what's going on just down the road over at NEOM, so appreciate that. Also, just the logistics here. I hope the audience is starting to formulate some tough questions for our panel members and speakers. Also, if you're online, go ahead and start typing those into the chat box so we can collect those for the discussion session, which will follow immediately after our last speaker. Speaking of which, Dr. Tim Allison is the Machinery Department Director at the Southwest Research Institute, SWRI, where he leads an organization that focuses on R&D for the energy industry. His research experience includes analysis, fabrication, and testing of turbo machinery and systems for advanced power or oil and gas applications, including high-pressure turbo machinery, centrifugal compressors, expanders, gas turbines, reciprocating compressors, and test rigs for bearings, seals, blade dynamics, and aerodynamic performance. So that's a partial reading of his biography, and I encourage you to see the website for the complete biographies for all of our speakers. But as you can see, he's well suited to discuss our next topic on the impacts of hydrogen transport in pipelines.
Great. Can you guys hear me okay? I see some nods. So well, yes. Good morning or good afternoon, and really appreciate the opportunity to talk to you today. As was mentioned in my bio, I'm a little different than the other speakers in that I'm a mechanical engineer. And so you're going to get a mechanical perspective on the impacts of hydrogen, transporting it in pipelines. And specifically, I'm going to talk about compression technologies. So on the right-hand side of this title slide, I'm showing cross-sections of different types of compressors that are used in the natural gas pipeline infrastructure and which would be adaptable to hydrogen pipelines, which include turbo compressors or high-speed centrifugal compressors, where you have multiple impellers that run on a shaft to compress a fluid, or a reciprocating compressor where a crankshaft actuates a piston, and that piston creates volume reduction and pressure ratio directly. And so both of those types of compressors respond a little bit differently, or are applicable to different parts of different flow rates or pressure ratios, which becomes applicable for hydrogen. Just a little bit about my research institute. So I don't work at a university. I work at a private, not-for-profit research institute. An aerial view of our facility is actually shown here. Let me go to the laser pointer. In the middle. And we do R&D on different kinds of energy systems within my department. A lot of it's focused around large-scale labs and testing. So we actually run test loops with both these types of compressors here, including hydrocarbons and maybe in the near future, hydrogen blending with hydrocarbons. Let's see. Okay, so let me just introduce from my perspective why hydrogen blending or hydrogen pipelines are of interest. And fundamentally, it comes down to the value case for hydrogen is really in energy storage and transport. So we have very low cost renewables that we're trying to use to decarbonize. They're not available all the time, and their peak availability doesn't coincide with peak usage in many cases during one day or even during throughout a whole year. And so we've got to find a way to store very large amounts of energy for very long periods of time, months, seasonally. And there really are not many technologies out there that can store for that long and that can run very large scale systems like a gigawatt scale power plant. Most of the energy storage schemes that do that are either hydrogen or hydrogen carriers, as was described by Mani. So I think that's the real value here is hydrogen is something that can be made and then stored and transported around. Pipelines are attractive, especially in the US, for example, where we have long distances between cities, especially maybe our solar farms are located far away. And we're trying to, we're used to being able to move energy around quite easily and cost effectively. We've actually done a study comparing hydrogen pipelines and natural gas pipelines and even electric lines for transport. And although the costs for hydrogen transport exceed that for natural gas pipelines, they're still cheaper and more efficient than moving that power around electrically. So there's still a value case there to transport hydrogen in pipelines. And the thought behind blending is that you don't have to go 100% right away. You could start introducing hydrogen into an existing pipeline infrastructure. So there's a lot of studies that are looking at how you do that. It's not easy. So there's several considerations that I'll talk through the rest of the day. Hydrogen, the way that at least the US pipeline infrastructure works is it's all very interconnected. So once you start putting hydrogen in one place, it's really going to get everywhere. So you have to worry about the compatibility of many, many end uses that are used to working with natural gas and will need to accommodate hydrogen. There's also questions about, where are we going to put the hydrogen or how are we going to introduce hydrogen into the system? Will it be introduced in batches throughout the day when it's being produced? Or will it be stored and then introduced at a constant rate? And that actually has a big impact on the compression machinery or piping for compressor stations along the pipeline. And I'll explain why here in a moment. So if we're going to be introducing hydrogen non-uniformly, there are many impacts to the equipment. I just want a quick note that there is actual experience with hydrogen pipelines, not just in the US, although that's what I'm focusing on here. There are also hydrogen pipelines in Europe. They primarily serve the petrochemical industry, so it's hydrogen as a product. But there is a pipeline shown here along the U.S. Gulf Coast, and even very large-scale hydrogen storage associated with that pipeline. So I've shown an aerial view of a salt dome cavern where large volumes of hydrogen are stored to buffer between use on the pipeline and production. So the pipeline operates at pressures ranging between 250, 1400 psi. It's relatively small compared to a natural gas pipeline, at least the larger pipelines, so 8 to 14 inches. Larger natural gas pipelines are going over 40 inches in diameter, so moving a lot more energy. At the relatively small scale that these pipelines operate at, they're typically driven by reciprocating compressors. So there is a lot of experience there. Let's see. Okay, I don't like to go over too many equations, but I'll throw a couple at you. In terms of compression, these are the fundamental thermodynamic equations that apply. I'll start with on the right, some of the properties of hydrogen. So I'm plotting the specific heat in red dashes, the specific heat ratio in orange dashes, and then the density in a blue line. And that's as a function of hydrogen blended into natural gas from 0% hydrogen to 100% hydrogen. So as we add hydrogen to a natural gas mixture, the density actually goes way down. Hydrogen's a small molecule. And the specific heat goes way up, order of magnitude. And the specific heat ratio stays about the same. So what does that mean in terms of compression? This is the equation, regardless of the type of compressor, of how you get pressure ratio through work. So on the left-hand side is pressure ratio. It's a function of the compression efficiency, the specific heats in the denominator, the work or the head rise is shown here, and the specific heat ratio is here. So when you change from natural gas to hydrogen, the specific heat ratio is about the same. What really changes is the specific heat goes way up. And so what that means is that if you want to get the same pressure ratio as the specific heat increases by an order of magnitude, you've really got to do a lot more work with enthalpy rise to get the same amount of pressure rise. The other thing to note, how do you do more work? Well, work is related to power. So we've got look at mass flow times power as work. In a centrifugal compressor, there's another equation that we use to determine work, and that's related to the impeller rotating speeds. That's U is the tip speed of those impellers, and then C is actually the gas speed exiting the impeller or entering the impeller. And so that shows if you want to increase the work in a centrifugal compressor, you have to do that by increasing the tip speeds with the same number of stages. There's another option where you just add more stages running at the same speed, and that'll get you an increased work per stage. So that leads to some challenges in hydrogen compressors. The other point is about density. So the density goes way down as you add hydrogen. So even though hydrogen is more energy dense on a mass basis, at pipeline conditions, it's actually significantly less energy dense on a volume basis. Compressors are all volume flow machines. So as you increase the required volume flow in a pipeline, it goes up by a factor of about 3. Then you're going to need larger compressors or compressors in parallel to handle that kind of volume flow. Meant to hide that one. So we did a study actually analyzing blending in a pipeline case study. We looked at several different pipelines, and I'm showing just an example chart from a very large pipeline that's transporting gigawatts of energy flow. And we looked at how does that affect the compression requirements of the system. One of the first things you have to ask yourself when you start talking about converting from natural gas to hydrogen is what are you trying to maintain? In a pipeline, you can maintain the volume flow. As I mentioned, that'll reduce the energy content. You can maintain mass flow. You can also do what we did in our study, which is say the energy demand is not going to change. So we maintain the energy flow. And when you do that, you end up with the increased compression work. It's not just because of the lower mole weight and the specific heat that I talked about. It's also because as you increase velocities in an existing pipe, pressure drop goes up. So you have to work harder to compress it to begin with, and you work harder to make up for the higher pressure drop. And that resulted in a pressure or power increase, as you can see on the right here, from 0% hydrogen up to near 100% hydrogen. We see almost a 6-to-1 or a 5-to-1 increase in power. So it's quite significant. That affects, with the gas turbine drivers or motor drivers are driving it, and regardless of the compressor architecture. An interesting side effect of that is you get a trade-off, because if you're using gas turbines to drive your compressors, which most pipeline stations in the US do, you're needing to add more compression power, which requires more fuel consumption, but you are using a lower carbon fuel as you start to blend in hydrogen. And so we looked at what are the CO2 emissions coming out of these compressor stations as you blend hydrogen in. And initially, the answer is that it goes up. The power requirements outpace the carbon reductions for having hydrogen in the fuel gas until you get to about 65% hydrogen. At that point, you're about 2.5 times the CO2 emissions from your pipeline drivers. And then from there on, at 100% hydrogen, of course, you go to zero carbon emissions. I do want to note this is only looking at the transport CO2 emissions. So, of course, you're moving hydrogen, there's an end use, and that makes the picture better. But where do you draw your boxes on emissions regulations? Hydrogen blending will have some impact on the pipeline stations themselves. So here's a chart comparing centrifugal compressors and reciprocating compressors. And here we're not changing the compressors at all as we add hydrogen from left to right. We're simply maintaining them operating at their design point. For a centrifugal compressor, that's operating at a fixed speed, fixed suction conditions, pressure and temperature, and the same inlet volume flow. So not changing the machine at all. And we're looking at what would change as we add hydrogen to the system. One of the most, you see the purple and the blue lines, which are the mass flow on blue, and then the energy content or heating value in purple. Those decrease significantly as you add hydrogen. As I said, the volumetric energy density is much lower. And so that goes down to values of near 10%, what it would be with natural gas, or down to about 30% of the energy content. The pressure ratio would also go down. Like I said, from the pressure ratio head rise equation. So that's the red line here, and we'd not be able to produce as much pressure ratio without changing something about how we're operating the compressor or adding more compressors to the system. A reciprocating compressor operates a little bit differently. So its design point would be a fixed speed, suction conditions, and pressure ratio. Like I said, this is not a turbo machine, but it operates through volume reduction and meets the pressure ratio imposed by the pipeline. And in this case, the energy flow change is comparable. So that's just driven by the characteristics of hydrogen relative to natural gas. The volume flow going through the machine would change a little bit. That's related to efficiencies and flow through the valves, the check valves that exit the cylinder. And the driver power required to run this compressor would change just a little bit, or reduce actually by about 10%, but not a significant change. So interesting to see. I think the conclusion, though, is, of course, if you want to maintain energy content, we're going to add a lot of compressors. A couple of last comments, and then I'll wrap up. Pipelines are also flowing acoustic systems. And some of our work at Southwest Research deals a lot with solving acoustic problems at compressor stations. So I mentioned a lot about compression power, but the hydrogen is also very different than natural gas in that its speed of sound is much higher. And so as you look at acoustic phenomena in pipelines, that can have a big impact. Acoustics affect pipeline operation and reliability through things like vortex shedding off of stub tees. And you end up with a vortex shedding frequency, which is a function of geometry. And if that frequency matches an acoustic frequency, which is associated with the speed of sound, you can run into resonant issues and high vibrations. And so as you increase the speed of sound, we have to look at changing those interferences that could affect designs that exist out there. The only nice thing about it is if you're maintaining energy content, the velocity increase, which governs the vortex shedding equation, goes up somewhat comparably with the speed of sound. And so if the ratio between the two may not change a lot. The other part where acoustics come in is in pulsations for recip compressors. So that big piston that's pushing the gas through introduces pulsations into a piping systems, and those can excite acoustic resonances. Recip compressors typically come with pulsation control systems attached to them or designed for them. And that design process really creates a natural frequency associated with the pulsation control system. It's a function of the speed of sound and then different geometries. And the design practice is to design for a pulsation, a filter frequency that's much lower than the operating speeds of the compressor. And that way, there's a lot of cutoff of the acoustics at the compressor excitation order. And so there's some words there. I'm just going to talk about it in pictures, though. So a typical frequency response of the pulsation filter positions the frequency quite low, below the operating orders. So 1 times running speed, 2 times running speed, etc. of the recip compressor. The blue bars around those running speeds just reflect that many recip compressors run at variable speed. So typically you don't ever want these to overlap, otherwise you'll end up with severe piping vibrations. As you move that speed of sound up for hydrogen, the same design of an existing acoustic filter will move up, and you run into areas where those frequencies may overlap. A couple of the last things on gas compression systems. There's a lot of coolers, scrubbers, vessels, valves, etc. We expect that there will be other changes needed to a pipeline compressor station to accommodate hydrogen blending. If you're increasing volumetric flows, then coolers will become less effective because they have less time to affect their heat transfer. Coolers are also sized, assuming in some cases that there's a temperature drop across valves through Joule-Thomson cooling. As you blend hydrogen in, the Joule-Thomson coefficient decreases in amplitude, so you get less cooling. So now you're hitting a double whammy on your coolers where you've got higher flow velocities and you've got to achieve more pressure or temperature drop because you didn't get as much out of an upstream valve pressure drop. So scrubbers also they're designed for flow velocities. So as we rapidly change flow velocities, we'll need to add scrubbers or at least evaluate their impacts. That's not really all of the impacts, but it was what I could do in about 15, 20 minutes. Happy to take questions with the rest of the panelists. Thank you.
Thank you so much, Dr. Tim, for bringing us up to speed on the important engineering details of transporting hydrogen. At this point, we'll start with some questions. I have one for you, Dr. Tim. So you mentioned, I think, in your last slide, if the welds are not necessarily heat treated, that brings up the issue of compatibility with hydrogen. What type of materials changes, if any, are necessary for transporting hydrogen in the existing pipelines and using the existing equipment that's currently used for natural gas?
Yeah, that's a great question. It's one that I skirted around in my presentation because I'm not a materials scientist. But there is a lot of work going on with evaluation of materials. I mean, one thing I'll say is there's a lot of experience operating in high hydrogen environments in refineries and so on. So that's not an unknown. But those materials and the operating practices for those refineries are very different than how a natural gas pipeline works. A natural gas pipeline is designed to codes that have been formulated over the years to address many of the range of operating scenarios that are needed. Refineries operate to a recommended practice rather than a code, and so that they operate with selected materials per that recommended practice, but they also have frequent inspections, etc. Again, it's operated very differently than a natural gas pipeline is. So there's general challenge as we look at suitability for materials because the RP, the recommended practice, doesn't necessarily apply to how a pipeline works. in general, hydrogen embrittlement affects higher strength steels, et cetera, worse. So there's, again, questions of what do we have to do to the materials in the natural gas pipelines? Do we operate at lower pressures? Do we have to derate the system otherwise? And it's very case by case. And that's about the best answer I can give without bringing on a materials expert.
Okay, that's great. Thank you very much. I'd like to thank our speakers for their excellent presentations and also for being concise and keeping us on schedule. At this time, I'd like to open up to the audience for questions. So if anyone here, I appreciate the audience that we have today here at the KAUST. And thank you for staying through all these presentations, and hopefully you have some questions for us if that some of our speakers can answer. Well, in that case, maybe you can think of one while I ask another one. Question for Nick. It's been a little while since you've spoken. Hopefully you're still alert there. Just a general question that people always have is, are hydrogen vehicles safe? And if they are, why are they safe?
So, so it's the age-old, is something safe question, and that's one of those that we try to avoid an answer on that, because is it safe, or can it be used safely? I think it's the latter. There certainly are a lot of good design considerations looking at the hydrogen system itself. So type 4 tank, typically, like on a light duty vehicle, would be a type 4 tank, which is a polymer liner with a carbon fiber overwrap for strength. They're provided, so you have this high pressure vessel with, inside of that vessel is a valve. That valve will shut off when the vehicle is turned off or power is lost to the vehicle. So it isolates that high pressure hydrogen inside the storage tank. The tanks, so downstream of that, there's a regulator, and downstream of that, hydrogen is flowing at much lower pressure, a fairly low flow rate. In an incident, an accident scenario, for example, if there's a hydrocarbon pool that is exposing the fuel cell tank, the fuel cell car with the tank, there's a temperature activated pressure relief device. That device will open up and vent that hydrogen before the vessel can rupture. So that, like all storage vessels, one of the significant hazards is the stored energy in that vessel. And so the hydrogen in this case is almost secondary to that vessel being ruptured and releasing all that energy content very quickly. So a lot of work's been gone into that, and so far the record is really good. Those type of tanks have also been used for compressed natural gas, and the safety record is pretty good with those as well. Very few incidents.
I guess that was my next follow-up question is, there's tens of thousands of these fuel cell vehicles on the road currently. Do you know of any accidents that have occurred with these tanks, or hydrogen fires, releases?
So there have been some accidents. We have some panel members, one that was in the early days of testing on the Toyota Highlander fuel cell vehicle. They were rear-ended pretty hard, sort of the tank sort of hanging on by its piping. They got the tank back to the shop and were able to start it back up, and it lost no hydrogen in the process. So I have not heard of any fuel cell vehicles. There have been accidents, but I haven't heard of any where there's been a significant release or loss of that containment, or even a venting. So I'm not aware of any.
Well, that's good to know. It's a pretty good track record so far.
It is.
So it looks like we're getting some great questions from online. Before I go to those, I just want to give our in-person audience one more chance to ask some questions of our panelists. So any questions from here? All right, well, if you think of any, let me know, we'll jump right in. So the first question from online is someone, Shashwat, hydrogen being buoyant is supposed to rise up in case of a leak. What happens when it burns? Does its flames, water also rise up? People say that actually avoids too much damage in case of fires. Please enlighten me on this.
Yeah, so So the bottom line is here is fire will, in the right concentration, that flame will actually propagate in a downward direction. This is what causes a lot of the overpressure and the damage. So, while the gas will tend to move up, its ignition, those flames can actually move down. And certainly typically above 6 to 8% is when you start getting those damaging pressures. So, and then, the other side of the equation here is those pressure effects. So high pressure vessels, if there's a leak, it's going to flow in whatever direction that is. If it's horizontally, it could flow some distance. There was an explosion in the US and in North Carolina a few years ago, in which that gas flowed horizontally and mixed in with some piping and equipment, and ended up having a deflagration and then a jet flame fire after that. And that kind of an incident in that circumstance that's not unusual to see that sort of thing when you have that kind of a leak. So no, it doesn't just rise up and away, and it avoids the damage in case of fires. And keep in mind, when you get to that point where you have a deflagration or detonation, those pressure waves are moving in all directions and will cause damage.
Okay, that's important information for us to know. Next question, looks like a great question for our professor. Is there any research done for hydrogen to be stored as a solid?
Yeah, I think it's a good question. And also there's another question later on about metal hydrides. I think they're related. So hydrogen, I don't think we'd ever freeze it to a solid, but when we say solid, typically we're referring to metal hydrides or solid-based storage mediums. So metal hydrides have been investigated since probably the 80s and 90s. Magnesium hydride, lithium hydride, these are common metal hydrides, and yeah, they're essentially solid state, say, storage of hydrogen. And even more recently, we see some research groups coming out with magnesium hydride powders. So the powder is essentially a solid state form of hydrogen. The challenge with metal hydrides is the gravimetric density of hydrogen. They're fairly low, below 5%. If you want a vehicle application, you want the lightest weight possible storage medium. As we heard from Nick, it's compressed gas in a carbon fiber composite tank. And you have about twice the hydrogen on a gravimetric density compared to a metal hydride. Still, people are looking into this. The economics are not so favorable. The weight is an issue. One of the new areas of research the DOE is looking at, conventional metal hydrides are less interesting from the Department of Energy due to the low gravimetric density. Their target is, I think, about 14 to 15% hydrogen per kilogram of material. So conventional metal hydride cannot reach that, but borohydrides can. So magnesium borohydride, sodium borohydride. So now you add boron in addition to the metal, and you can store more hydrogen. And they can reach the gravimetric density targets stated by the US Department of Energy, but the challenge with those is very slow kinetics. So they're able to, they store quite a bit of hydrogen, but getting the hydrogen out is very slow. It's not a rapid process like an LOHC or ammonia cracking or depressurizing a cylinder. So this is a relatively new area. I'd say about 10 years old, borohydrides. People are looking a lot about how to increase the kinetics so you can get very fast removal of hydrogen. And it's yet to see where that goes.
Well, sounds good. Thanks for the Zoom attendee for the question, and thanks, Professor Manny, for your answer. Looks like you tagged the next question. Yeah, go ahead, please.
Yeah, so in addition to the metal hydride work, there's actually some work going on at NASA and University of Central Florida on using aerogels to store hydrogen. That's through an adsorption process, and there's an aerogel that's nanoporous, so it has very high surface area per volume. It essentially will hold on to hydrogen at cryogenic conditions, and then as you let it warm up, it releases the hydrogen. So there's some work going on there as well.
Sounds fascinating. It's a great, looks like we have a question from our
Yes.
audience.
For many. So you mentioned there is a technology called the LHC where you attach your hydrogens to a things like toluene, right? So when you dehydrogenate the compound, so where do the toluene goes? I mean, does it like recycle or get
Yeah,
spent or?
the general, there's no operating LOHC facility over long distance transport yet, but the general concept is, yeah, you would have a bulk carrier of carrying a methyl cyclohexane from Saudi to Germany or to Italy, and then you would offload the LOHC, and then you'd have terminals where the LOHC, the hydrogen is removed, and then you'd regenerate toluene and hydrogen. The toluene would then go on a ship back to Saudi. So you have to cost in the shipping of the material both ways, actually.
Oh. And another question is about the pipeline. So many mentioned that it's quite expensive to build a pipeline. So does it share the concerns in the US?
I think maybe Tim can answer that.
Yeah, so it is more expensive than a natural gas pipeline. But from the numbers that we've seen, I mean, electrical transmission is also quite expensive. You've got to build towers or bury the lines, and the high voltage lines, their costs are quite high as well. So we see comparable costs, but better efficiencies with pipeline transport for hydrogen.
Yep, thank you.
Thank you, Carson. This is for Nick. My name is Chris Meyer. I'm the safety officer here in Clean Combustion. And I had a question is like, one of the big issues I've always seen is, because originally I'm a pharmaceutical scientist, so I used to do wet chemistry, but we're doing a lot of engineering applications. And a lot of these people are used to working in discovery labs where it's like one cylinder. But then we start getting into these issues where they start doing these small pilot plant things that actually can get kind of large. I'm just kind of curious, what kind of issues have you seen with the scale up of hydrogen processes, experiments? Because this is one that always, I know our authority having jurisdiction, it always freaks them out because when they see a cylinder, they're like, okay, great. When they say, no, we want to bring a trailer full of hydrogen, then they start getting really nervous and things. But is there any certain considerations that you know of or references to discuss about the scale up of the use of hydrogen?
Yeah, great question. So we have seen the scale up cause lots of problems. Certainly probably one of the most significant issues that we had seen in recent years was an explosion at the University of Hawaii in which the gal ended up losing a limb as a result, and they scaled up in that experiment. And I think part of the challenge here is that it's the familiarity. Working with the smaller quantities and smaller conditions, it's very familiar, but most folks don't realize it. Move into more of a production phase or a larger process phase that really needs to be more thoroughly evaluated. So I would say anytime you do a change like that, you should go through a formal MOC process, management of change process, and really a good, strong HAZOP, FMEA, what if analysis would be a little bit weaker, but certainly a good risk analysis process would be important to ensure that you consider all the conditions and activities. And the other side of the equation on this is moving that hydrogen when you get into larger quantities, moving that outdoors and manifolding it and bringing it in that way instead of bringing that storage inside. We've seen some conditions where they've brought that larger storage quantities into the facility, and it's created some serious risks and hazards. So it's one of those subjects we probably could talk about for about another half an hour, but just real thoroughly do a risk analysis for that activity and make sure that all people that are going to be involved in the activity, and operations and safety experts and hydrogen experts are a part of that analysis. And I did see there was another question on unique considerations to be taking a risk assessment studies. So if you don't mind, I'll just cover that real quick.
Yeah, please go right ahead.
Okay, thank you. So it really comes down to the use, but those key parameters or the key properties of hydrogen that make it unique. The small molecule, the embrittlement, those are very important. The other is that when you get into things like electrolysis, you've got to start realizing you now have multiple hazards. The oxygen being produced can be a hazard in itself, and many times can be more of a hazard than the hydrogen, especially at the larger electrolysis activity. So really important just to go through and make sure that as you're looking at the different parts and pieces. The other, and let me jump back, one of the other parts that we routinely see problems with in the HAZOP level, the risk analysis level is not doing a very good job, is on the vent systems and manifolding those vent systems together and not evaluating pressures and fittings, and that can cause some real issues as well.
Thank you very much. Moving on to the next question. It looks like it's been tagged by Professor Manny. If pipelines were to be built in KSA, would blue hydrogen and green hydrogen be blended for export? Assuming green hydrogen is expensive, but it is clearly cleaner, how will that influence cost and perception?
Yeah, it's a good question. Again, all hydrogen is the same color. There's no color. And it doesn't, from the pipeline's perspective, I don't think it cares if it's green or blue. And it's actually though interesting thing. I've heard this being discussed in conferences where they're discussing financing and imports and exports of and policies related to hydrogen. And the most rational way of thinking about it is, yeah, you'd have one pipeline infrastructure for regardless of the source of the hydrogen. You just have to meet, of course, quality standards for the purity of hydrogen going into that pipeline. And yeah, blue hydrogen, green hydrogen shouldn't make a difference. There'll have to be some kind of blockchain, let's say, set up, monitoring of how much of each type of hydrogen goes into that pipeline, because different markets will price that hydrogen differently depending on the carbon footprint related to its production. So we know the Europeans are becoming quite, let's say, philosophical about the type of hydrogen that they want. But that may not be everywhere in Europe, the same legislation applied. And maybe some parts of Eastern Europe will take blue hydrogen. The Japanese, for example, the South Koreans, they don't seem to be so dogmatic about the color of the hydrogen in the next 10, 15 years. They want to build the infrastructure. They want to build the demand and build the hydrogen economy, even on blue hydrogen today, even potentially gray hydrogen. So I think the rational way of thinking about it is if a hydrogen economy, or I'll say a low carbon, decarbonized economy is the aim in the future, we look first at building the infrastructure and lower cost forms of hydrogen, such as gray hydrogen and blue hydrogen, will facilitate and underwrite the development of that infrastructure and lower the cost to the customer in the end. And then in the long term, when hydrogen prices from renewables comes down, they can leverage on that infrastructure.
Yes, that sounds great. That sounds like a great approach for implementing the energy transition. Just one more question for Professor Manny, then we'll switch to a different panelist, I promise. The question is, do you have any insights on the end-to-end efficiency of the different hydrogen transportation methods? Yeah,
so of course, pipeline, I think, and compressed, let's say standard compressed storage and transport is 700 bar, or even pipelines at 100 bar. They're fairly efficient. I think 90% plus efficiency. Ammonia, it's in the range of, you got to produce your ammonia, that's about 90% efficient, and transport, boil off losses, and reconversion, you might lose another 10, 15%. So I think total efficiency on ammonia, when you considering how much hydrogen you lost, is about 75 to 80%. And then LOHCs are similar, they're around 70% because they need more heat. It's more endothermic to remove the hydrogen from the LOHC, so about 70% end-to-end efficiency. But if you use waste heat, provided you have waste heat, then that efficiency is upwards of 85, 90%. So again, it depends, of course, a lot on the context where we're going to use that material at the end, what energy we're going to use to recover the hydrogen afterwards. But I'd say, purely efficiency perspective, anything besides pipeline is in the range of 70 to 85%. But we don't always choose things based only on efficiency, right? It's often on cost. And sometimes the less efficient options are actually less costly, and more efficiency means more cost.
Okay, thank you. Actually, I wanted to kind of follow up with my own question on that for Dr. Tim. You showed, the recompression stations, the cooling stations in the pipeline. Is this, in your opinion, the approximate efficiency of the pipeline? What is the efficiency loss in those stations and such along the way?
Yeah, I'm trying to recall the numbers again, because it depends on how long the pipeline is. So it's better to think of it as an efficiency per kilometer or per mile. They're on the same order that Mani said. So I think for a longer pipeline, you could get to around 90%. But again, it depends on how long it is.
Okay, thank you.
I did put a link in the Q&A. There was a question about the paper, so I tried to link to it, the ASME paper that I had cited.
Okay, thank you for that. And I also noticed put up your contact info, so anyone after this, feel free to contact the speakers directly if you have any further questions. I think you might have covered this, but the question for Nick: what are some of the unique considerations that need to be taken during PHA risk assessment studies for hydrogen processing facilities?
Yeah, that was the one I tagged on at the end. So
okay.
Feel free,
Okay.
and feel free, to those in the audience, feel free to reach out if you have some other questions in that area. I'd be happy to answer them offline.
Now, let me throw the questions back to the audience. Any more questions from the live audience here? All right. So going back, I think I'll skip this one. Dr. Tim, for a sustainable approach, these impellers for hydrogen transport needs to be, again, powered by renewable electricity, right? Such things can be powered by wind energy, and maybe especially for pipelines running across waters. What are ways to power the hydrogen transport systems?
Yeah, that's a great question. So, the way they do it with natural gas is just they pull fuel from the pipeline in most cases. At least, in the U.S., there are many remote pipelines that don't have strong grid connections. And so people are looking at the same thing for hydrogen blended pipelines, or maybe even hydrogen pipelines. There's a lot of work going on at advancement of gas turbines so they can blend percentages up to 100% of hydrogen in their fuel. There's really two classes of gas turbine combustors. One is a conventional combustor or a diffusion flame combustor. Those already run at very high hydrogen concentrations up to 100%. The disadvantage, though, is you get high local temperatures inside those combustors that increase NOx production. And so you run up into NOx emissions limits there. Most modern combustion systems are premixed, so they premix the air and the fuel. That does a better job of NOx mitigation down to the ppm level. But when you're premixing your air and fuel, you then have the risk where hydrogen can flash back. The high flame speeds of hydrogen will eventually exceed the flow velocities through the injectors, and the flame will come up into your part. And of course, bad things happen. And so in order to develop low NOx combustors for high hydrogen applications, there's a lot of development work going right now. So I think gas turbines are still possible drivers in hydrogen pipelines. Gas engines can handle hydrogen as well, at least up to certain percentages with changes in their control systems, and they're developing higher hydrogen capabilities. Electric motors could be purely electrically powered, but in order to run those motors, you've got to get an electric line out there of adequate capacity. So it depends on how remote the pipeline is, on how realistic that is.
Great. Those are some interesting answers to some things that I hadn't really thought about. It's good to know. One more question for Professor Manny. How is NEOM planning to power the hydrogen transport systems? Similar to the last one, but maybe slightly different.
As I assume you're referring to like the infrastructure for actually transporting the hydrogen, like the pipelines or the vehicles. These will all be either battery electric. Well, vehicles will probably be hydrogen electric, the ones that are moving hydrogen around. And anything on pipeline or grid powered will be powered by the renewable energy grid. Now we might have some microgrids that are based on fuel cells. So off-grid applications, which are not connected to the main NEOM grid, will be based on fuel cells. Those fuel cells will have to have some parasitic losses associated with the hydrogen transport and storage infrastructure that's there. So you might lose about 5 to 10% of your hydrogen due to these parasitics related to the storage and the transport of the hydrogen in your local off-grid location.
All right, sounds great. Well, it's been a great afternoon discussion here. Just want to thank the speakers once again for your time and effort and great presentations. Also, our in-person audience, thank you for attending today. And I'd like to also thank Dr. Mohammed and the CCRC for inviting me to be the moderator today. At this time, on behalf of the CCRC, I'd like to close this session and thank you once again.
Thank you.
Bye-bye.